Okay, we're back. I moved to a different classroom to finish the rest of this practice test, so this will be part 2 for the practice test for test 3. Recall that I don't really have control over the volume on this camera, so if you can't hear me well, you're going to need to turn the volume up on your computer. If I'm coming across as too loud, then you can turn the volume on your computer down to adjust to a comfortable volume level. Also remember that you need to have your practice test for test 3, the cheat sheet to the practice test for test 3, and the solution key to the practice test for test 3. All 3 of those documents are on eCourse. We left off this is going to start the second part, or the remaining part of this practice test. We left off in part 1 of this video when we were doing problem 4, part C. And this involves the very first occurrence of an event when you're doing a sequence of n independent trials, and you're looking for the first trial in which the first occurrence of the event occurs, or in this case, for 4 part C, it says what is the probability that if you draw continuously with replacement a card from a sufficiently shuffled deck of 52 cards, what's the probability that you'll draw an ace for the first time by your third draw? And as we said last time, to find the probability of the first occurrence of an event by a certain trial, it's a compound statement. So this actually means, what's the probability that I will either draw my ace for the first time on the first trial, which is the formula from the first row of table 1F on your cheat sheet, or I draw my ace for the first time on the second trial, which is the formula for the second row of table 1F on your cheat sheet, or that I draw an ace for the first time on the third draw. So saying what's the probability that you'll draw an ace for the very first time by your third draw is actually a compound statement that says what's the probability you either draw your ace for the first time on the first draw, or you draw your ace for the first time on the second draw, or you draw your ace for the first time on the third draw. So you have to use the formal addition rule for mutually exclusive events here, and instead of just using the formula from the third row, which is 1 minus little p squared times little p, you have to calculate the formula for each row from the first row to the third row in the table, and then add those formulas together. So this will give the probability that you draw your ace for the first time on the first draw. This will give the probability of drawing an ace for the first time on the second draw. And this last part gives you the probability you'll draw an ace for the first time on the third draw. And also recall from the last video at the end that since it says what's the probability you'll draw an ace for the first time by the third draw, the capital N here is 3. So we're using the first, second, and third rows of the table 1F on the cheat sheet. And our little p here, which is the probability you'll draw an ace in any one given draw, we discovered that from problem 3A to be 1 over 13. So this is the setup. Use the probability formulas from the first, second, and third rows. If you said something like, what's the probability that you draw an ace for the first time by the fourth draw, you would have to add another term, and you would have to add the formula from the fourth row to this, and you would actually have a sum of 4 terms, 1 for each of the first 4 rows. So in this case, since it's by the third draw, we just have a sum of formulas from the first 3 rows. Now all we have to do is plug into that the value little p is 1 over 13 everywhere you see little p in this. Okay? So now we're going to substitute in the value 1 over 13 in everywhere there's a little p. And if you have a graphing calculator like you all do, you can put all this in at one time on your calculator. You can put 1 over 13 for little p plus 1 minus 1 over 13 in parentheses times 1 over 13 plus 1 minus 1 over 13 squared times 1 over 13. And if you enter all that correctly into your calculator, you could press enter. And after that, you should be getting on your calculator that this comes to approximately 0.2135. If you round to 4 significant figures, it rounds to 0.2135. So the probability that if you draw continuously until you get an ace for the very first time from a shuffled deck of 52 cards, the probability that you'll draw an ace for the very first time by the third draw is 0.2135 as a decimal rounded to 4 significant figures. And like I said, all these calculations can be found in the solution key to the practice test for test 3. Alright, so we're done with problem 4. Now I'm going to temporarily skip problem 5 for now, because as you may recall from class, the material you need to cover for problem 5 on the practice test, which is about expected value, that material is the last topic in the supplemental notes for chapter 16 that's currently posted on eCourse. I'm leaving that as extra credit on the test. Since we did miss some classes and we were pressed for time, it's still in the notes that are typed and on eCourse. The material for that problem, which is called the expected value, is the last topic in the notes from chapter 16, and you can read that. There are several worked out example problems in those typed notes of problems just like problem 5 on the practice test. I will come back and do problem 5 on the practice test at the end of this video, since that's the problem which now counts as extra credit for test 3. So we will skip problem 5 for now, and we'll come back to problem 5 at the end of the video and do that last. And then you'll have a problem very similar to that on the test, which will be your extra credit problem on test 3. So we're going to go ahead for now and skip right on to problem 6. And for problem 6, we start the confidence interval problems. So that's the part that comes from chapter 20 and 21. Now, if you go to problem 6, this is the part that comes from chapter 20. And this is where you're going to do a confidence interval estimate for an unknown population percentage using a sample percentage or sample proportion and a given sample size and a given confidence level. Then we're going to determine the margin of error for that inferential study, and then subtract the margin of error from the sample proportion, add the margin of error to the sample proportion, and then at the given confidence level, we'll have a confidence interval estimate for the unknown population percentage. So let's write down the given information for this confidence interval estimate. What's given is, it says, suppose that Bill is one of the candidates running for a state Senate seat in some U.S. state. And also, these are hypothetical. I made these up. This isn't real. Shortly after the voting booths close in the state, the results of an exit poll are given, in which a random sample of 2,378 voters were asked who they voted for. So the sample size for this study is 2,378. That's the number of members in the random sample. It says, of those 2,378 members of the random sample, 1,275 of the sample members said they voted for Bill. So that says X, which is the number of members from the sample in the relevant category here, that being those that voted for Bill, is 1,275. And the confidence level is 99.7%. So we're computing a confidence interval estimate for the actual percentage of voters that voted for Bill in this election at the confidence level of 99.7%. Now we're going to go to the cheat sheet and use the step-by-step method that has the embedded formulas we need for how to do a hypothesis test for an unknown population percentage. So if we go to the cheat sheet, look in section 2 of the cheat sheet, we see that, first of all, they give you a chart in there that tells you the different corresponding critical values, Z alpha over 2, that go with the various confidence levels. If you look at that chart that tells you the critical value for a confidence level of 99.7, it says in the cheat sheet there that that critical value is Z alpha over 2 equals 3.0. So that's the critical value, Z alpha over 2, that corresponds to 99.7%. If we look at step 1, the first thing you do is compute what's called the standard deviation. Oh no, the first thing you do actually in step 1, excuse me, that I'm ahead of myself. The first thing we do is we use X and N to calculate the sample proportion. That's the proportion of the sample that said they voted for Bill. And we call that P hat. So our sample proportion, which is the proportion of all members of the sample that said they voted for Bill, would then be X over N. And we'll round that to 4 significant figures. And X over N here turns out to be 1,275 divided by 2,378. And if you use your calculator now, we see that that comes out to be 0.536. Rounded to 3 decimal places. So, and that's of course the same as saying 53.6% as a percentage of the members of the sample said they voted for Bill. Now, make sure that all got in there. Okay. Let me move this over a little bit. Okay, so you can see it all in there. Now, I'm going to have to erase to do step 2. And like I said, if you're following along with the solution key, all these calculations are in the solution key for test 3. For the practice test for test 3. So now, moving on to step 2. So this was P hat, sample proportion. And now for step 2, we calculate what's called the standard deviation for this problem. And the standard deviation is given in step 2 by the formula square root of P hat times 1 minus P hat, all divided by little n. It's the square root of all of that. So this is the formula from the cheat sheet for step 2. And we just computed P hat in step 1 to be 0.536. So now we just, if you have a graphing calculator, this will all get plugged in one step. You can take the square root of, and then plug in 0.536 times, and then in parentheses 1 minus 0.536, and then all of that's divided by the sample size n, which is 2,378.